curves and is added to it along with the correction factor to account for the types of the drain. Then this model is expressed in the terms of L. This can be given by L50 dV is equal to free space path loss AMU. There are the two parameter F and D, frequency and separation distance, gain, height of the transmission antenna and height of the effective receiver antenna. This is the gain of which is taken at the height of the effective transmission antenna, and it is the gain of the effective receiver antenna. And one more data are also factor is here, that is the G area. This G area is a correction. It is this is known as correction factor, because when the delayed signal which is due to reflection and diffractions are not reaching at the receiver and the total path loss has been changed, because we are only taken the line of sight path loss and we are not include this correction factor. It is totally depend on the area where the effective local environments are effect on this delay. So the path loss is also increased due to this factor. So the total equation which is given by in terms of L50 dV is equal to LF plus AMU FD and G of HTE minus G of HRE minus G area. This is a known as the Okumura developed a set of curves giving the medium attenuation relative to the free space in an urban and the over a quasi smooth drain. So the first term which is written as L50 dV is known as 50% of percentile median value of the path loss, and LF is nothing but it is the free space path loss. AMU FD, it is the medium attenuation relative to free space. This is the median attenuation relative to the free space, and this is the base station and antenna height gain factor. This is the mobile station antenna height gain factor. So we have right here, this one is the base station antenna height gain factor. This one is the mobile station antenna height gain factor. Now where the where now where where the where we have consideration our notes, where now we have taken the values. It is very difficult. We have write the L50. It is the percentile. 50 percentile, that is nothing but median. The value of this is value of a propagation path loss, and LF is the free space propagation path loss, where a mu term F comma D is median attenuation relative to free space, and GH of T, it is the base station antenna height gain, antenna height gain factor. One more term is GH of RE. This is the important term, and this is the mobile station antenna height gain factor. Okay, and last term which is used, that is the correction factor. This is gain due to the type of environment. It is the correction factor. This and this values AMU and G area is values are directly taken by with the help of this Okumura graph, and others values are we calculated. So let us rewrite once again formula. L50 percentile is LF plus AMU F comma D minus G H of TE minus G H of RE minus G REA, and this is the Okumura path loss equation, and the factor which is are calculated with this formula is 20 log H of TE divided by 200 and H of RE 10 log HRE divided by 3 and HRE 20 log HRE divided by 3. Here one thing is, see, we having the two values of GHRE. One is the 10 log H of RE by 3 and another is the 20 log HRE by 3. So that it is the gain factor is decayed by the 20 dV GH of T, and HRE affected by the two constant. It is the height of, when the height of receiver antenna is less than 3 meter, then we take the 10 log H of RE by 3. When the height of HRE is more than 3 meter but less than 10 meter, then we use this formula. So it is the basically height of the antenna, and the transmitter height is lies between 1000 meter 30 meter. This is important formula for calculating the numerical point of view, and also to calculate the L50 dV. So correction factor are directly values taken by from the graph. So Okumura model is wholly based on the measured data and does not provide any analytical explanation. So Okumura's model is considered to be among the simplest, best in terms of accuracy in the path loss prediction. So it is the accuracy path loss, or this it is a very practical and has become a standard for the system planning in the modern land mobile radio system. So this is the one, there is a one disadvantages over Okumura model is the which is now we have considered as a major disadvantage with the model is that the slow response to the rapid change, slow response to the rapid changes in terrain. Therefore the model is good in only for the urban area or suburban area. It is good for only urban and suburban area, but it is not good for not useful for the rural area. It is not good for the ruler. This is the disadvantages of this you can say this model. And consider the one more thing is that in a Okumura model, the correction may also be applied in a Okumura model. So the some of the important terrain related to parameters are the terrain undilutions height. So the isolated heights, average slope of terrain, and the mixed land sea parameters. So once the drain relative parameters are calculated, it is necessary to add the correction factor, or you added or you subtracted as your requirement. All these correction factor also available on a Okumura curves. Okay, now take a one example. We have one example. Example is here is one example. See the students, I am taking this example. Here example is, now see, find the median path loss using Okumura model for the distance is 50 kilometer and height of h of te, that is the base station height, is 100 meter. Mobile station height hr is 10 meter in a suburban environment. Okay, if the base station transmitter radiates as EIRP of 1 kilowatt, EIRP of 1 kilowatts at a carrier frequency of 900 megahertz. So find the EIRP in dBm and the power at the receiver where the gain at receiving antenna is 10 dB. Now once again we have reread this question. Find the median path loss using a Okumura model for d equal to 50 kilometer, h of t is 100 meter, h of r is 10 meter in a suburban environment. If the base station transmitter radiates as EIRP of 1 kilowatt at a carrier frequency of 900 megahertz, find EIRP dBm and the power at the receiver where gain at receiving antenna is 10 dB. So this problem is based on Okumura model, and in Okumura model what we have till now, we having the distance d50 50 kilometer, h of t 100 meter, that is the height of the transmission, this is the height of the receiver 10 meter, and one more thing is given, ERP of 10 kilowatts, and the frequency f is carrier frequency 900 megahertz is given. So find the values of this receiving power, and when the receiving antenna is gain of 10 dB. So let us move on our main. Here this is our main equation. L 50 dB is equal to LF plus AMU. LF is the free space path loss. AMU is the attenuation factor, which is two parameters. One is the frequency, other with suppression distance. This is the gain factor, antenna height gain factor. This is the antenna height receiver antenna factor. This is the correction factor G area. So taking this formula and solving the problem, when L is given 50 dB is equal to LF plus AMU F comma D minus G H of TE minus G H of RE minus G area. It is like this. This is equation. And now calculate LF. LF is what? LF is what? Can you read the LF? Calculate the LF. LF is minus tan log lambda square 4 pi square d square. This is the LF, and lambda is C by F. F is given 900 megahertz. L is given 900 megahertz. 900 megahertz. So calculate the lambda. 3 into 10 की power 8, 900 into 10 की power 6, and put it here in this equation. Free path loss 3 into 10 की power 8 divided 910 की power 6 whole का square divided by 4 into 3.4 whole square. Okay, and distance between given D is given 50. D is 50 kilometer. So convert it is into meter. So what is, after the calculating, it's come